Hello everyone, and welcome back. Today's video lecture will be covering the Aqueous Equilibrium chapter. This will be labeled as either Chapter 17 or Chapter 18, depending on which version of the book you have. This chapter dives a little bit deeper into equilibrium, and it talks about some special aspects of equilibrium when we're talking about aqueous solutions. First topic we'll cover is the common ion effect. So we'll start with a definition. What is the common ion effect? So the common ion effect is the shift in the position of an equilibrium after adding a substance that provides an ion in common with one of the ions already involved in the equilibrium. What this means is that it's sort of a special type of the Chatelier's principle, only this time we're dealing with ions. So if you remember, the Chatelier's principle tells us that a reaction at equilibrium will react to a stressor to balance out that stressor. Well, in this case, the stressor is either adding or removing an ion. So if we take a look at this reaction, here we have acetic acid reacting with water to form an equilibrium between H3O plus and the acetate ion. So what we look to answer with this section is what ions are present. Well, here we have H3O plus and we have the acetate ion. Obviously, acetic acid and water are not ions, but here we have H3O plus and we have the acetate ion. We don't know what happens to this equilibrium if either of these ions are added. So for instance, if we add H3O plus or if we add acetate ion, what's going to happen to this reaction? And lastly, what happens if we try to establish this equilibrium where either of these ions are already initially present? So if you think back to your ice tables, we always started from only having reactants and no products. Well, what happens if we add some product and some reactant at the same time? Okay, so we're going to start out with an example. So just an example of the common ion effect. So the question says, the pH of a 0.10 molar acetic acid with a Ka of 1.8 times 10 to the minus 5. So the pH of that solution is 2.89 at 25 degrees C. And they want us to calculate the pH of a solution that is prepared by dissolving 0.10 mole of acetic acid and 0.10 mole of sodium acetate in enough water to make a 1 liter solution. So in this problem, they're telling us the pH of a 0.1 molar acetic acid solution is 2.89. This means that all we've done is we've taken acetic acid and we dissolved it into water. And they give us a temperature just to let us know that this Ka corresponds to room temperature. What they want us to do is they want to say, well, okay, well, what if instead I add the same amount of sodium acetate, or the same amount of acetic acid, excuse me, but I also add this amount of sodium acetate ion. Okay, then they give us a volume here so that we can convert everything to molarity. So the first thing we have to do is we have to think about, okay, what am I trying to calculate here? I'm initially trying to calculate pH, which means I need to calculate this, the H3O plus concentration. So I'm going to take a look at my equilibrium reaction here. So I have acetic acid reacting with water to give us H3O plus and the acetate ion, so that very first reaction we looked at. Okay, and to do this, we're going to set up an ice table, just like the ones we set up before. The only real difference here is that instead of just starting from reactants, I'm also going to start with some product in place. Okay, so I'm going to use my Ka, just like I did before, and an ice table to initially solve for x and understand what x means. And I'm going to find the H3O plus concentration. So let's start just by filling out our ice table. So set it up just as you normally would, writing in your reactants and your products. And again, we can ignore water since it's a pure liquid. Let's just fill in like we would. So we know we're starting from 0.10 molar acetic acid. And we're also starting from 0.10 molar of the acetate ion. Okay, we're starting with no H3O plus. So I didn't say that we're adding any H3O plus. It just said we're adding sodium acetate, which is an acetate ion source. So those are the two reactants that we have. So we start from no of the H3O plus or none of the H3O plus and a little bit of the acetate ion and a little bit of acetic acid. So how did I know these two concentrations? So they were nice enough to put this in a 1 liter solution, which means all we had to do was take the number of moles and divide by 1 liter since we're talking about moles per liter. In this case, since we are in just 1 liter, the molarity will be equal to the number of moles we add. Okay, so we have 0.1 molar, and then over here we also have 0, since we're starting from nothing, and here we have 0.1 molar. Okay, and we're going to look at our change line. So our change line we're going to calculate just the same as we would have before. Okay, so here we have our acetic acid going away since it's becoming H3O plus and an acetate ion. And then our product side, we also have H3O plus building, just as we would have before. So we're going to say plus X. We have the acetate ion, which we're assuming is going to build since we're forming H3O plus. So we'll also have plus X here. And again, our acetate has a minus X. So we're going to set this up exactly like you would have with the ice tables before. Only this time we're starting with some of our product. That's the only real difference. Okay, so then we calculate our equilibrium line. So exactly the same as you would have done before, just total up the different columns. So here we have 0.1 minus x, here we have just x, and then here we have 0.1 plus x. So just like we would have done it before. Okay, then we're going to set up our Ka expression. So remember that Ka is equal to the product of our products over the concentration of our reactants. So here we have H3O plus times the acetate ion over acetic acid. Okay, we're going to use the same Ka since we're talking about the same temperature. So now we just need to put this in terms of x. So we have x times 0.1 plus x and 0.1 minus x. So we don't want to go through, and if you remember before I showed you the quadratic expression, we can just use our assumption again. Okay, so since we have a relatively small Ka, we can use our expression and we can assume that 0.1 plus x and 0.1 minus x are approximately 0.1 and 0.1. Okay, so this makes our life a lot easier, and you'll find that if you calculate it both ways, you'll get relatively the same answer, so there's really no need to go through all the math. Okay, so again, just solving for x like we would have before. So essentially what we're saying here is that 1.8 times 10 to the minus 5 is equal to, we have x times 1.0 over 1.0, so really that's just equal to x. So here, our expression becomes 1.8 times 10 to the minus 5 is equal to x. Okay, so remember that x, if we go back to our ice table, x in this case is also equal to our H3O plus concentration. So we can say this. We can say that x is equal to H3O plus, which is equal to our Ka. Okay, so what they're asking us for is to calculate the pH. Well, now we have the H3O plus concentration. So all we really have to do now is remember that pH is equal to minus the log of H3O plus. Okay, so take minus the log of 1.8 times 10 to the minus 5, which gives you a pH of 4.74. So everything was exactly the same as we did on our previous ice tables. The only real change here was just to add some of our product. Okay, so we started with some acetic or some acetate ion, but everything else was the same. And you notice that in all reality, it didn't have that big of an effect on our actual answer. The only time it would have an effect is if these two numbers were different. So if I had something like maybe 0.2 over 0.1, something like that, then it would change our answer. Okay, so it won't always be like this. Okay, so the question here is, why did the pH increase? So if you remember, our pH before was something like 2.5, 2.89. So that's just for acetic acid by itself. Okay, but we add some acetate ion, and now suddenly our pH has increased. So we want to try to answer the question, why did the pH increase? To answer this question, we have to go back to the Chatelier's principle. So the addition of the acetate ion to a solution of acetic acid suppresses the dissociation of the acid. So you can think about it this way. So before, when we talked about Le Chatelier's principle, we talked about either adding reactants or adding products as a stressor. So in this case, we're adding a product. Okay, so in this case, we're suppressing the ionization. In other words, we're suppressing the formation of products, or in other words, we're shifting the equilibrium to the left. So we're suppressing the dissociation of the acid by adding more of a common ion. Okay, so the equilibrium is going to shift to the left. We're going to have less H3O plus as a result, and therefore we're going to have a higher pH. So if we don't add any acetate ion, acetic acid will dissociate to its fullest extent, as much as it can given its Ka. Okay, so we're going to form a certain level of H3O plus. And remember that if we have more H3O plus, we have a lower pH. So here we're adding acetate ion, so we're adding a product. So we're going to shift the equilibrium to the left. So in other words, suppressing the amount of acetic acid that can form H3O plus. Therefore, we're going to have less H3O plus and therefore a higher pH. So really, this is just Le Chatelier's principle at work. Okay, so now I have a question for you to try. I'll read it first, then I'll give you some time to pause and work it out for yourself. Okay, so the question says, assume you have a 0.3 molar solution of formic acid, and you've added enough sodium formate to make the solution 0.1 molar in formate ion. So I want you to calculate the pH before and after adding the sodium formate. And they give you a Ka here. So what they want you to do is they want you to calculate a pH for just formic acid in water. And then they want you to do what we just did, where you add the corresponding ion, so the formate ion, and then calculate a new pH. Okay, so I'll give you some time to pause the video and work this out, and then we'll go over it. Okay, so hopefully you've gone over this problem. I will bring my paper back into view, and let's go over it together. Okay, so I know that I realize the reaction is a little bit covered, so I will rewrite it for you. Okay, so here we have HCO2H, formic acid, combining with water, H2O, and that's a liquid. So we have aqueous formic acid combining with water, and that's going to be in equilibrium, which is H3O plus with H3O plus. It's going to be aqueous. And also formate ion, CO2 minus, which will also be aqueous. And I'm going to zoom out a little bit so you can see a little bit better. Okay, so hopefully that's a little bit easier to see. Okay, and the first thing we want to do is we just want to set up our ice table. So the question is, the first part of the question is saying if you have a 0.3 molar solution of formic acid, and they want us to calculate the pH for that. They gave us a Ka, so our Ka that they gave us equal to 1.8 times 10 to the minus 4. That's our Ka. Right? So we want to set up an ice table for this problem. Since we're calculating pH at equilibrium, we need to use an ice table. So I'll just use the same reaction that I've written out. Okay, then I just have to fill it in. So we can put an X through the water because we know it's not involved with equilibrium. And what they're asking us is to just do this. So 0.30 molar formic acid. Okay, and we're starting from no H3O plus. And in this particular case, we're not adding any of the formate ion. Okay, so our formic acid is going to be reduced because it's becoming product. So we'll say minus X. Our H3O plus is increasing. And our formate ion, since we're also increasing H3O plus, is also increasing. Okay, so we have plus S and plus X on our product side and just minus X on our reactant side. Okay, so again, just total up the columns. So here I have 0.30 minus X. Here we just have X. And here again, we just have X. Okay, so from here, we need to set up our Ka expression in terms of X. So remember, Ka will be equal to concentration of the products, so H3O plus, times formate ion, over equilibrium concentration of a reactants, so formic acid. Okay, so now we just need to set this up in terms of X. So we're going to say that 1.8 times 10 to the minus 4 is equal to X times X over 0.3 minus X. Okay, here since I have a small Ka and I'm dealing with a weak acid, I can make my assumption, so I can make this simply equal to X squared over 0.3. Okay, so I'll rewrite my expression just to clean it up a little bit. So now I have 1.8 times 10 to the minus 4 is equal to X squared over 0.3. Okay, and now to solve this, I'll simply multiply both sides by 0.3. So these two will cancel, times 0.30. Okay, so if I do that math, I end up with 5.4 times 10 to the minus 5 is equal to X squared. Okay, then take square root of both sides, so square root of this And then taking the square root here gets rid of the square. So I end up with x is equal to 7.3 times 10 to the minus 3. And it's going to be in units of molarity. Okay, so this is my x. And then I have to remember, if I go back to my ice table, so what am I ultimately looking for? I'm ultimately looking for pH of this solution at equilibrium. So I want to know, what is my H3O plus concentration? So for this particular case, x is equal to H3O plus concentration. So I can say x is equal to concentration of H3O plus, which is equal to 7.3 times 10 to the minus 3. Okay, and I'm looking for pH. So pH will be equal to minus the log of 7.3 times 10 to the minus 3. Okay, and this gives me a pH of 2.13. Okay, so that's the first half of my answer. Okay, so I'll give you a second here where you can see the entire solution. You can pause the video if you need to. Okay, so now what they want us to answer is, what is the new pH if we also add 0.1 molar of the formate ion? So we're going to set up our ice table again. Okay, so I'll rewrite the reaction equation. So we'll say HCO2H, formic acid, plus H2O, water. Draw a line here just so we can see where the division is. It's in equilibrium with H3O plus and the formate ion. And this is all going to be aqueous except for water, which is a liquid. Okay, so now we need to set up an ice table. So we'll say ICE. Okay, so we're starting from the same amount of formic acid, 0.30. That's in terms of molarity. Still don't care about water in this case. Still starting with 0 H3O plus, but now we're starting with 0.10 molar of our formate ion. Okay, so here we're still reducing. So we're still taking formic acid, making H3O plus and formate ion. So we're going to say minus x. Here we'll say plus x, and here again we'll say plus x. So totaling up our columns, we have 0.30 minus x, just x, and then now we have 0.10 plus x. Okay, since we started from some formate ion this time, we have to include that in our equilibrium expression, or include it in our equilibrium line, I should say. So now we just set up our Ka in terms of x. So we'll do it exactly the same as we did before, so products over reactants. So I'm going to skip that step for now. I'm just going to fill it out. So now we have x times 0.1 plus x over 0.30 minus x. Okay, and again, we're going to use our assumption here, where we can assume that K is relatively small, and we can assume that this is approximately equal to x times 0.1 over 0.3. Okay, so we're basically forgetting about this plus x and this minus x, just to make our lives a little bit easier. Okay, so now we can set up that Ka is equal to, so same Ka, 1.8 times 10 to the minus 4 is equal to, or approximately equal to, we can say, x over 0. Or times 0.1 over 0.3. Okay, so now isolating x, we can just say that 1.8 times 10 to the minus 4 times 0.3 over 0.1 equal to x. Sorry if you can't read that, that's a 3. Okay, now we just have to multiply those two together. So we end up with x equal to 5.4 times 10 to the minus 4, which is also equal to the H3O plus concentration from our ice table. So if we want the pH, can you still see? Yes. pH equal to minus the log of 5.4 times 10 to the minus 4, which is going to give us pH of 3.27. Okay, so again, our pH went up. So just like we saw in the last problem, if we add some of the corresponding ion, it's going to increase our pH. Okay, so we went from a pH of 2.13 to a pH of 3.27. Again, so with Lechautier's principle about work, so we've added some product, and what that's done is that shifted our equilibrium to the left. So now I'll give you some time to have this on the full screen so you can see the whole solution. Okay, so moving on to the next slide here, we have another question. So this time we want to know the pH of a 0.25 molar acetic acid solution, and oh wait, I'm sorry, they're telling us the pH of a 0.25 molar acetic acid solution is 2.67. We want to know what is the pH of the solution if we have 0.25 molar acetic acid and 0.10 molar sodium acetate. In other words, we're adding acetate ion to an acetic acid solution. They want us to calculate what is the pH. Okay, and they gave us the Ka here, 1.8 times 10 to the minus 5. So I'll give you some time now to go ahead and pause the video and work this problem out. Okay, so I'll bring the paper back up and we can go over this one. Okay, so let's rewrite our reaction equation. So we have acetic acid reacting with water, which is in equilibrium with H3O plus, and of course the acetate ion. Let me just slide that over a little. Okay. So now the question is asking us to calculate the pH of the solution that's made up by adding acetic acid and sodium acetate, which is just an acetate ion source. Okay, so we're going to set up our ice table. So hopefully by now you can see in these type of problems when you need to use an ice table and when you don't. Okay, so if we're putting a stressor on an equilibrium reaction, you're almost always going to use an ice table. Or if we're just talking about equilibrium in general, hopefully that kind of triggers your mind to think ice table. Okay, so now we just need to fill in what we have. So the question told us we have 0.25 molar acetic acid, and forget about water. We're going to start with no H3O plus, of course. So before this has time to react, we of course start with no H3O plus. Okay, we didn't add any in according to the question. And we start with 0.1 molar acetate ion. Okay, so as normal, we have minus x here. So we're going to increase this. So we have plus x, and here we're also increasing, so we have plus x. Okay, so totaling up our lines gives us this. Okay, so again, remember we're after this x value. Okay, so we really want to know what is this H3O plus concentration. Remember that if you're asked what is the pH, what is the question really asking you? It's asking you what is the concentration of H3O plus, and then take the minus log of it. That's all the question's really asking. Okay, so we can set up our Ka expression. So they told us Ka for acetic acid is equal to 1.8 times 10 to the minus 5. Okay, you'll get used to that number. You'll see it all over the place. Okay, and now we want to set up Ka. So hopefully by now you can set up a Ka, but remember that Ka is equal to concentration of our products over concentration of our reactants. Okay. So now we want to set this up in terms of our x. Okay, so we'll write our Ka, 1.8 times 10 to the minus 5. I'm going to put our Ka expression in terms of x. So in other words, we're going to drag down our bottom line. Okay, so remember products over reactants. Okay, so here we have x times 0.10 plus x. Okay, remember it's plus x since we're increasing the concentration. A second for the video to catch up. and that's going to be over 0.25 minus x. Okay, so here again we have a situation where we have a plus x and we have a minus x. So again, what if we want to know, can we use our assumption or not? So I'm going to write it out this time. Since I've just kind of been saying it so far, I'm going to go ahead and write it out for you this time. Okay, so remember that we can say if the concentration of our acid over our Ka greater than or equal to 100, then you can use the assumption. So let's plug that in real quick. Okay, so the concentration of our acid was 0.25 molar, and our Ka 1.8 times 10 to the minus 5. So what does that give us? So I say 0.25 divided by 1.8 e to the minus 5. That gives me 1.39 times 10 to the fourth, which is definitely very much bigger than 100. Okay, so it's safe to use our assumption. So we can rewrite this, and I'm just going to jump down. So we can rewrite this to just say, so remember that what we're saying here is we can write this, x times 0.10 over 0.25. So I'll rewrite that down below. Okay, so we're just basically forgetting about the plus x and the minus x, since our Ka is small enough. Okay, so here we're saying 1.8 times 10 to the minus 5 is approximately equal to x times 0.1 over 0.25. Okay, so we'll multiply both sides by 0.25 over 0.1. So this will cancel, and this will cancel. So here we have 0.25 over 0.1 times our Ka, and that's going to be approximately equal to our x value. Okay, so that gives us 4.5 times 10 to the minus 5 is approximately equal to x, which is equal to the concentration of H3O+. Okay, so remember what we're after in the question is the actual pH. So now we'll say pH is equal to the minus log of 4.5 times 10 to the minus 5, okay, which gives us a pH equal to about 4.35. Okay, so our original pH from the question was 2.67. So we've added some acetate ion, and look what we have. So we have Le Chatelier's principle, increasing our pH. Okay, so I'll pull this back down so you can see the ice table. So you have a good idea. Okay, then I will show you all of the work down below. Okay, so that's where we came from, and that's where we ended up. Okay, so that's using ice tables when we have with the Chatelier's principle, basically. So what if we add some of the common ion? How it's gonna affect our pH? Okay, so let's move on to the next section, which we'll be talking about buffer solutions. Okay, so we'll start out with just our definition of a buffer solution. So what is a buffer solution? You've probably heard this term before, and you've probably used one, although you probably wouldn't know necessarily. Okay, a buffer solution is a solution which contains a weak acid and its conjugate base, or a weak base and its conjugate acid. So either way, you just need an acid-base pair. Okay, and it resists the drastic changes to pH. That's the key here. So a buffer solution is a solution made up of either a weak acid and its conjugate base or a weak base and its conjugate acid. And it's going to resist changes to pH. That's the big key here. So a buffer solution resists changes to pH. Don't forget that. Okay, so here we have it drawn out a little bit. So we have a weak acid and a conjugate base. So for example, some pairs. So we could have acetic acid and the acetate ion. So just like the problem we just looked at, we could have HF and fluoride ion. We could have the ammonium ion and ammonia. Okay, we have HPO4, H2PO4 and HPO4, 2 minus. So again, just a weak acid and its conjugate base. So HA and A minus. Let's look at how they work. Okay, so if we have a buffer solution, so here we have hydrofluoric acid being added to water to give us H3O plus and fluoride ion, of course. Okay, so now below we have two bars. Okay, so we have this more blue bar represents the fluoride ion, and the pinkish bar represents hydrofluoric acid. Okay, then we have that drawn as sort of a picture down here. So we have all HF, you can kind of think of it that way, and we also, we have HF and F minus. Okay, so what we want to look at is what happens to this solution if we, for instance, what if we add H plus? Okay, so what's going to happen? Why does it resist change to pH? So remember that if we're adding H plus, traditionally that would lower our pH. Since we're adding H plus, we're going to increase H3O plus concentration. Therefore, we're lowering our pH. So what happens though? So here, if we add H plus, what's going to happen? So it's going to combine with F minus to give us more HF. Okay, so the solution, the buffer solution, is absorbing that added H plus. So we're shifting our equilibrium. So just like we looked at before, so if we add a common ion, we're going to shift the equilibrium one way or the other. In this case, we're adding a product common ion, so it's going to shift our equilibrium to the left. So the solution essentially is absorbing the H plus. Okay, then down in the picture down below, you can see that we have a little less F minus and a little more HF. Okay, so we've decreased our amount of F minus slightly, as you can see by the dotted line, and we've increased the amount of HF also by the same amount. Okay, so that was if we add an acid, so if we add H plus. Okay, well what happens if, for instance, we add a base, OH minus? Well, it's going to be a similar thing. So here we're adding OH minus, that's going to take a proton from our HF, giving us more F minus and less HF. But again, it's not going to change by that much. So again, the Chalais principle tells us that if we're going to remove one of our reactants or products, we're going to shift the reaction to balance for that. So here we're removing HF, okay, and we're forming more F minus. And you can see that on the picture down below, the same is true. Okay, so the big takeaway here is just that these buffer solutions resist changing pH by absorbing the ion that's being added. Okay, so let's kind of look at a real life example here. So here we have a solution of hydrochloric acid, relatively dilute. So here we have 1.8 times 10 to the minus 5 molar solution of hydrochloric acid. And it's going to have a pH of about 4.74. So then if we take a pipette, and if we, for instance, add 0.1 molar sodium hydroxide, and here we've added some indicator that's good for this pH range. Okay, notice that we changed the actual color of the indicator. And as well, we've changed the pH. So we've gone from a pH of 4.74 to a pH of 5.4. Okay, and then our indicator has changed color as a result. Okay, so this would be an example of a non-buffered solution. So what if instead we have a buffered solution? So here we have 0.1 molar acetic acid and 0.1 molar sodium acetate. This buffer solution will have a pH of 4.74. And what's going to happen if we add either an acid or a base to it? So here we're adding the same base again, sodium hydroxide, same amount, same concentration. Okay, well here actually we're adding 100 ml. In our previous example, we only added just a few drops. So here we're actually adding 100 ml, so a lot of acetic acid, or a lot of sodium hydroxide, excuse me. Okay, and notice that the indicator doesn't change. So we're staying at the same pH, so our indicator doesn't change. So again, this is a solution, a buffer solution, resisting changes to pH. Okay, in this next section, we're going to talk about the Henderson-Hasselbalch equation. So suppose you wanted to calculate the pH of a buffer, or suppose you wanted to prepare a buffer at a certain pH. How would you do that? Or suppose you wanted to calculate how a buffer would change when adding either an acid or a base to it. Well, you're going to use the Henderson-Hasselbalch equation. Okay, so we're going to look at our same acid-base pair here. So we have acetic acid combining with water to give us H3O plus and the acetate ion. So we've become familiar with this by now. Okay, so we have an acid being added to water, giving us H3O plus and a base. So we know that our Ka is going to be equal to concentration of our products over the concentration of our reactants. So Ka will be equal to H3O plus times the concentration of our base over the concentration of our acid. Okay, so in other words, we can rearrange this to say Ka is equal to concentration of H3O plus times concentration of base over the concentration of the acid. Okay, so we're kind of building this equation as we go. Okay, so now this is where we left off. Okay, so what we can do is we can take minus the log of everything in the equation. So we can say minus the log of Ka minus the log of H3O plus. And then we can also take minus the log of the concentration of the base over the concentration of the acid. Okay, so what have we done essentially? We've taken, well, we can rearrange this, of course, to be minus the log of H3O plus is equal to minus the log of Ka plus the log of the base over the acid. So all we've really done here is added plus log of base over acid, okay, to both sides. Okay, and the reason we do that is because this gives us a useful form of the equation. So what we really have here is we have the Henderson-Hasselbalch equation. So we have pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. And this is the useful form of the Henderson-Hasselbalch equation. And you can rearrange it if you need to, but this is the most commonly used form. Okay, so make sure you know this equation. So what this allows us to do is allow us to do something like this. So we can answer this question. So we want to know, what is the pH of a buffer solution that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate? Okay, so we have our acid-base pair. So a weak acid and its conjugate base. And it's asking us, what is the pH? Okay, so in this particular case, we know the Ka, we know the concentration of the acid, and we know the concentration of the base. We're just looking to solve for pH. So we can use our Henderson-Hasselbalch equation and just plug in everything that we know. So we're going to say pH is equal to minus the log of our Ka, that's our pKa, remember, plus the log of the concentration of our base, 0.1, over concentration of our acid, 0.12. And now all we have to do is plug those numbers into our calculator, and that will spit out the pH. Okay, so here we have the pKa will be 3.85 minus the our plus the log of our acid over our base over acid becomes plus minus 0.08. Okay, so just totaling that up, we get a pH of 3.77. So our Henderson-Hasselbalch equation allows us to calculate the pH of a buffer solution. It also allows us to calculate the ratio of base to acid that we need to prepare a certain buffer solution. So for now, let's try using the Henderson-Hasselbalch equation to solve this problem. So the question says, calculate the pH of a buffer solution that is 0.45 molar in ammonium chloride and 0.15 molar in ammonia, I should say. Okay, then they give us a Ka for the ammonium ion. Okay, so see if you can use the Henderson-Hasselbalch equation to calculate the pH of this solution. Okay, so let's jump back over to the paper and work out this problem. So again, it's asking us to calculate the pH of this buffer solution given these two concentrations of our base and our acid. So right away, this should trigger to use Henderson-Hasselbalch equation. pH is equal to pKa plus the log concentration of our base over concentration of our acid. Okay, so now we just have to plug in what we know, and they also give us a Ka. So Ka equal to 5.6 times 10 to the minus 10. Okay, so now we're looking to calculate pH, so we don't even have to rearrange the equation. So all we have to do is plug in what we know. So minus the log of our Ka will give us our pKa. You can solve it and then plug it in if that's more comfortable for you, or you can just write it out like this. Plus the log. Okay, and then they gave us these two numbers as well. So the question tells us, the important thing here is knowing which one is your acid and which one is your base. Okay, so remember that the 0.5 here, the ammonium chloride, that's going to be our NH4 plus. Okay, so that's going to be our acid form. Okay, so the other needs to be our base. So here we have 0.15 over 0.45. Okay, and those are both in units of molarity. Okay, so this will cancel out. Okay, so this ends up being pH equal to 9.25 plus a negative 0.48. So our pH will end up being 8.77. Okay, and that's all the question asks us to do. Okay, so really not too hard once you understand what you're doing. So the toughest part there was probably deciding which is the acid and which is the base. So here what you need to recognize is that NH4Cl, ammonium chloride, that's our ammonium ion source. So that's going to be NH4 plus. Okay, so it has an extra proton, so that's going to be our acid, whereas ammonia will be our base in this case. Okay, so I'll give you a second if you need to pause the video and write this down. Hopefully you had most of this done already. Okay, we'll move on to the next slide. If you want it digitally, you can have that as well. Okay, so another question for you. So this one asks, if we have 2 grams of benzoic acid and they give us a molar mass, and 2 grams of sodium benzoate and they give us a molar mass, and they're saying they're dissolved in enough water to make 1 liter of solution. They want to know what is the pH of the solution, given that the Ka from benzoic acid is 6.3 times 10 to the minus 5. Okay, so it's a very similar problem. They're asking us to calculate pH, but we have to do a little more work. So this is sort of a realistic example of how you would use this. Okay, so if you go to the lab and you're trying to prepare a buffer, you would need to measure out your different supplies, your different chemicals, to form your actual buffer solution. So you would probably start out by saying, okay, so if you're a biologist, maybe I need, a certain buffer solution that's going to maintain whether you're growing cancer cells or something like that, but you want to use a buffer so that those cells don't get destroyed or whatever biological material you're using doesn't get destroyed. Or maybe you're a chemist just working with buffer solutions. Okay, so you would probably solve for the ratio, and we'll look at a couple of those in a second, but eventually you're going to have to go measure these out. Okay, so here they're giving you 2 masses, and they're asking you to calculate the pH of the solution. So you'll need to first use the molar mass to convert to moles, and then use the fact that it's a 1 liter solution to convert to molarity. Okay, and then plug those into the Henderson-Hasselbalch equation, and that'll tell you the pH. So go ahead and pause the video and try to work that out. Okay, so let's try to work this one out. So again, the first thing we have to do is convert from grams to a concentration. So they gave us 2 grams of each chemical. They gave us the molar mass of each. They told us we have a 1 liter solution. So first let's calculate moles, and let's convert those moles to a molarity. Okay, so the concentration of our acid, so we'll start with the benzoic acid. You could start with either one, doesn't really matter. Okay, so they gave us 2 grams, and they gave us a molar mass. Okay, so you can set up your dimensional analysis. There are 2 grams, and that's going to be for every 1 mole of the acid, I have 122.1 grams per 1 mole. And this is going to be for the benzoic acid. I'll just write Ba for short. Okay, so this gives me 0.0164 moles of benzoic acid. Okay, now I need to do the same for the base. Well, let's convert to molarity first. Okay, so here we have 0.0164 moles. They gave us a volume of 1.0 liters, so it just so happens to turn out that this is also 0.0164 molarity, and that's for HA or BA, however you want to look at it. Okay, now let's do the same for the base. Okay, so we'll say the base concentration is equal to, they gave us 2 grams, okay, and they gave us a molar mass, so we'll do the exact same calculation, only we have a different molar mass this time, so 144.1 grams per every 1 mole. This is of our A minus, just to keep track a little bit there. So this gives us 0.0139 moles, And again, since we just have 1 liter, that's going to be equal to 0.0139 molar. So that's over 1 liter. Okay, so now we have our two concentrations. So the only thing left to do is to plug these into our Henderson-Hasselbalch equation and calculate the pH, since that's what we're being asked for. Okay, so we'll say the pH is equal to the pKa plus concentration of the base. I'm sorry, plus the log concentration of the base over the concentration of the acid. Sorry, that's a little bit sloppy there, but hopefully you can tell what it is. Okay, so now we just need to plug in our numbers. Okay, so here we'll say pH is equal to minus the log of the Ka they gave us in the equation, on the question, 6.3 times 10 to the minus 5. Okay, it's going to be plus the log, and now we use our two concentrations that we calculated. So first we'll take the base, 0.0139, over concentration of our acid, 0.0164. Those are both molarity. Okay, now I just have to do the math. Okay, so this will be equal to 4.20 plus minus 0.0718. So adding those two together, we end up with a pH equal to 4.13. Okay, so there you can see the entire solution. Again, if you have any questions over these, please feel free to email me. Come to my office hours, my virtual office hours. Go see the SLC online. Whatever you can do to get help if you need it. Okay, so let's move on back to the slides. And we'll talk about, well, what range is a buffer good for? So obviously you probably can assume that I can't add an infinite amount of an acid or a base to a buffer, right? So they have some usable range. And we refer to this as being the buffer range. Okay, so the buffer range is the range of pH values over which a buffer system works effectively. Okay, so if I have too strong an acid or too strong a base at a given buffer pH, probably not going to be that effective. And generally speaking, we try to make buffers for plus or minus 1 pH unit from the target pH. So if I want a pH of 7, I'm going to have a buffer, I'm going to try to make my buffer within 1 pH of that. Okay, so a buffer can maintain its pH as long as the ratio of the base to the acid remains the same. Okay, so if we mess up our log of our base over our acid too much, that's going to affect our pH greatly. So we want to keep those numbers relatively small. So there's a range in which this can work. So therefore, a buffer can even maintain pH if it's diluted. So actually, it doesn't matter if I have a very concentrated base or very diluted base, okay, as long as that ratio stays the same. That's the important thing here. Now, it may be less effective if I dilute it, but the pH will still be the same. Okay, so buffer range, remember that's just the pH values over which a buffer system works. Okay, so it's not necessarily talking about how much acid and how much base we can add. That's just talking about um, what will the pH be of that buffer solution. But if we start talking about buffer capacity, this is the amount of an acid or a base that can be neutralized by a buffer before there's any significant changes to the pH. Okay, so I kind of misspoke before. This is what I'm talking about when I'm talking about how much acid or how much base can I add to something. So I can't just infinitely add acid or base to a buffer without changing the pH, because eventually, going back to our Hasselbalch equation, so eventually, if you remember, we talked about this ratio changing as I add acid or a base, so it's being consumed, so the H plus is being consumed, or the A minus is being consumed, or the HA is being consumed. So to a point, I mess up this ratio. So if I add enough acid or enough base, I'm going to mess up that ratio. Okay, so that's going to change its buffer capacity. or that is its buffer capacity. So there's a limit to how much acid or how much base I can add. Okay, so what if I'm in the lab and I'm asked to, prepare a buffer solution, or I'm working with a project and I want to prepare a buffer solution? Okay, so how am I going to do this? So when I'm preparing a buffer solution, the best idea is to choose an acid with a pKa close to the target pH. Okay, so typically the buffer range is plus or minus 1 pH unit on either side of the pKa of the buffering agent. And generally buffers are prepared so that the base and the acid range from 0.1 to 1 molar. Okay, so let's look at some data here. Okay, so the question says, I wish to prepare a buffer solution with a pH of 4.3. And we're given a list of acids and base combinations down below. Okay, so the question wants us to say which combination of an acid conjugate base pair should be used. And they also want us to say what ratio of the acid to the base should be used. Okay, so here we have HSO4 and SO4 minus. Okay, then we have acetic acid, acetate ion. I have HCO3 minus and CO3 2 minus. Okay, so we have 3 weak acids here and their conjugate bases. They give us Kas. Okay, then we can find the pKa. Okay, and they tell us the buffer range. Okay, so first thing we want to know is which combination of the acid-base pair, which acid-base pair should we use? And then lastly, we want to know what ratio of the acid to the base should we use. Okay, so take a second to think about that first part. Okay, so we're looking for a pH of 4.3. Okay, and remember we want that buffer range to be plus or minus 1 of our desired pH. Okay, so it looks like the best buffer combination for this particular situation would be this guy. Okay, so we want a pKa close to our desired pH within plus or minus 1 unit. They were nice enough here to even give us the buffer range. Okay, but we could have figured that out just by adding 1 or subtracting 1. Okay, so it looks like this acetic acid pair is going to be the best. Okay, now the second part of the question wants us to say, okay, well, now that you know which pair to use, what combination should they be in? Okay, so take a second to see if you can figure out how to work that out. And when you're ready, come back and restart the video and we'll go over it. Okay, let's solve this one together. So now we know which combination we want to use. Now I want to know what ratio should they be in. Okay, so we chose. So we're going to say we're going to choose the acetic acid, CH3COOH, / acetate pair, CH3COO minus. Okay, so that's the pair we're going to choose. From our chart, we know that the Ka is 1.8 times 10 to the minus 5. Okay, and they tell us the pKa is equal to 4.74. Then the range is, of course, plus or minus that. Okay, so now we want to set up our Henderson-Hasselbalch, and we want to solve this time. So let's just write out our equation first. pH is equal to pKa plus the log of our base over our acid concentrations. Okay, so this time we want to solve this equation for this portion. Okay, because that's the ratio of our base to our acid. And that's what ultimately we're looking for. I mean, that's what the question asks us for. We just want to know that ratio. Try to get this to focus a little better for us. Okay, that looks a little bit better. Okay, so now we just plug in what we know. So we know our target pH from our question is 4.30. Okay, we know our Ka is 4.74. Then we're just going to say plus the log of our base concentration over our acid concentration. Okay, so now we need to solve this equation for this portion. Okay, so the first thing we want to do just minus 4.74, subtract 4.74 from both sides. Okay, so this will go away. So now we're left with minus 0.44 is equal to the log of our base concentration over our acid concentration. Okay, so remember now we just need to get rid of the log. So how do we get rid of the log? So we're just going to raise 10 to the power of both sides. Okay, so in other words, we're going to say 10 raised to this, 10 raised to this. We'll remove our log. Okay, so that gives us that 0.36 is equal to the ratio of our base to our acid. Okay, and that's our answer. So what this means is that we have 0.36 base for every 1 acid. Okay, so remember that. When you end up with a decimal like this, it's really saying 0.36 to 1. So remember there's actually a 1 under here. Okay, so that tells us our ratio. Okay, so these problems really aren't super complicated. You just have to understand what you're solving for and how to get there. Okay, so let's move on to the next slide. And we have another question. Okay, so this one wants to know what mass in grams sodium acetate, and they give us a molar mass, must be dissolved in 0.3 liters of 0.250 molar acetic acid to produce a buffer with a pH of 5.1. And we're going to assume here that the volume goes unchanged. And they give us our pK or our Ka here. Okay, so this time it's a very similar problem where we're going to want to solve for that ratio. Okay, but this time they're giving us the amount of acid, and they want to know what a mass in grams of the acetate ion do we need. Okay, so take a second, try to work this one out, and we'll go over it. Okay, so this problem we're going to have a similar setup, but our answer is going to give us a little bit different information. Okay, so we want a pH equal to 5.1. Okay, they give us sodium acetate and its molar mass. They give us a volume, 0.3 liters. They give us a concentration of 0.250 molar for acetic acid. Okay, I'd prefer to write it out that way. Doesn't really make a difference though. Okay, and they tell us a Ka is equal to 1.8 times 10 to the minus 5. We want to know what mass of sodium acetate. Okay, so we're going to start out by setting up our Henderson-Hasselbalch again. So pH is equal to pKa plus the log, the ratio of our base over our acid. Those are both our concentrations. Okay, so this time we know the concentration of our acid. They told us that, so we know this part. So what we're looking to solve for this time is the numerator. Okay, so we want to know what's the concentration of the base, and then therefore we'll know how many grams. Okay, so let's just plug in the parts of the equation we do know. Okay, so we have 5.10 is equal to minus the log of our Ka, 1.8 times 10 to the minus 5, plus the log of a concentration of our base, so this is our unknown this time, over, and we know the concentration of our acid this time, 0.250 molar. Okay, sorry about that. If you notice a bit of a time jump there, my using my cell phone as the camera for the paper, and even plugged in, this program uses so much power that it actually drained my phone completely. Okay, so starting back where we left off. So we were just setting up our Henderson-Hasselbalch with what we know. Okay, so let's just simplify this a little bit. So we can say 5.10 is equal to 4.74. That's our pKa plus the log of the ratio between our base concentration and our acid, which we already know. Okay, so now we just want to solve this for this log portion. Isolate that. Okay, so we'll subtract 4.74 from both sides. Okay, so this goes away. We end up with 0.36 is equal to the log of the concentration of our base over 0.250 molarity, concentration of our acid. Okay, so again, we're after this piece of information. We want to know what concentration of our base do I need. Okay, so we need to solve this. We need to get rid of this log. In other words, I can't really do anything with the log right now. I just need to get rid of it. So I'm going to say 10 raised to the log of this side, or 10 raised to that side, and then 10 raised to 0.36. Okay, so that's going to give me something like this. So if I say 10 raised to 0.36, I end up with 2.29 is equal to concentration of my base over 0.250 molarity. Okay, so again, I'm looking for this piece of information, concentration of my base. So I'm going to multiply by 0.250 molarity. This goes away, and do the same thing on this side, 0.250 molarity. Okay, so I end up with 0.57 is equal to concentration of my base in molarity. So this is molarity. Okay, so that's the concentration of my base, assuming, okay, so remember this is in molarity, so what this really is moles per 1 liter. Okay, but I'm not after a whole liter. Okay, so the question tells me I want 0.3 liters. Okay, so if I rewrite this out, I have 0.57 moles in 1 liter. Okay, so to get rid of those liters, I can multiply times 0.3 liters, just the volume that we have. And that's just over 1. So this will tell me the number of moles. And this gives me 0.171 moles of B minus, or in other words, or A minus. So my acetate ion. Okay, so I'm still not quite done. Now I need to use my molar mass. So this tells me how many moles. So I'll start from there, 171 moles, A minus. And now I can use my molar mass to put that into grams. Okay, so my molar mass for sodium acetate, so this is sodium acetate, so I should say NaCH3COO. Okay, so now I know the number of moles, so now I'll use, okay, so sodium acetate, just relabel everything a little bit. Okay, so now I can use my molar mass, so 82.0 grams are in 1 mole. Okay, so this gives me a total of 14.02 grams of sodium acetate. Okay, and that's what the question is asking me for. So that would be my final answer. Kind of a roundabout way of getting there, but that's one way you can use the Henderson-Hasselbalch equation. Okay, so I'll show you the first part again. And I'll show you the bottom part again. Okay, so that gives you an idea of the entire solution. Okay, so let's go back to the slides. We'll move on a little bit. Okay, so suppose I wanted to know how many pH units, or what pH, how much pH a buffer would change. Okay, so suppose I add an acid or a base to a buffer solution, and I want to know how much would the pH change. Okay, so here we have a question. So it says a buffer is made by adding 0.3 moles of HC2CH3 CO2, that's acetic acid, and 0.3 moles of sodium acetate. And we add enough water to make 1 liter of the buffer solution. The pH of the buffer is 4.74, so roughly acetic acid pKa. They want us to calculate the pH of the solution if we add 0.02 moles of sodium hydroxide, and they gave us the Ka for acetic acid. So how are we going to solve this one? Okay, so we need to separate these into two separate calculations. First, we have a stoichiometric calculation to determine how much of the buffer is consumed by adding the acid or the base. And then secondly, we can use the Henderson-Hasselbalch equation to determine the new pH. Okay, so these look somewhat like ice tables. Okay, so the first part is just figuring out how much of our buffer is consumed. Okay, so it's sort of like an ice table, but you notice here we have IACF. Okay, so initial, and notice we're in moles now, we're not in concentration. So we have to, in order to use this type of system, we have to put everything in terms of moles. Okay, so that everything is equal. Okay, so remember, you can't subtract molarity from molarity. You have to subtract moles from moles, or add moles to moles. Okay, so we have initial, we have the added, change, and then final. Okay, so we set these up almost exactly like an ice table. It's just a little bit different. Okay, so our initial line, so if we go back to our question, it tells us we're starting from 0.3 moles of acetic acid and 0.3 moles of sodium acetate. Okay, so we'll just fill that in. So at this point, we've added no OH minus, and again, we can ignore water since it's a pure liquid. It's not really affecting our reaction anyway. Okay, so now we want to add what we've added. Okay, so looking at the question again, we're adding 0.02 moles of sodium hydroxide. Okay, so that goes in the added line. Okay, so we're adding sodium hydroxide. So now what we need to decide is, how is this going to affect our reaction? So we have to say that the 0.02 moles of sodium hydroxide will react with 0.02 moles of the acetic acid to produce 0.02 moles of acetate. Okay, so this is what I mean. Okay, so notice here that we are adding, so in our added line, we say we're adding 0.02 moles, but then we're subtracting it. Why are we doing that? Because it's being consumed by the acetic acid. So remember, we're in a buffer solution, so we have some acetic acid, we have some acetate ion. So we're adding a base, so it's going to consume some of the acid to give us more of the acetate ion. So here we're going to say we're not adding any of this, we're not adding any of this, but we're adding sodium hydroxide, which will then be consumed by the acid. Okay, so we're going to reduce the amount of acid we have by the same number of moles, but we're forming new acetate ion. Okay, so we're adding 0.02 moles of the acetate ion. Okay, so then we need to total up these columns just like we do with an ice table. Okay, so we end up with something like this. Okay, so assuming there's no change in volume, okay, we still stick with 1 liter. Okay, so we take that many moles divided by 1 liter gives our new concentrations. We need these concentrations to plug back into our Henderson-Hasselbalch equation. So this is what we call the stoichiometric part. So all we're doing here is we're looking at how much adding that base, how much acid did that consume, and how much acetate ion do I have now. So how much acid do I have left over, and how much more acetate ion do I have? So how much total acetate do I have in the solution? Okay, and then just convert those to concentrations at the bottom. Okay, now the second part, we're going to use our Henderson-Hasselbalch. So remember, Henderson-Hasselbalch is the pH is equal to the pKa plus the log of the ratio between the base and the acid, which is what we just found in the last slide. Okay, so we can set this up. Okay, so remember, pKa for acetic acid is 4.74, so just minus the log of the Ka. Okay, so we can set this up. So we can say pH is equal to 4.74, the pKa of acetic acid, plus the log of my base concentration over my acid concentration. Okay, so just solve for this. We end up with a new pH of 4.8. Okay, so our pH changed from 4.74 to 4.8. Okay, so it's changed a little bit because we have changed our ratio slightly, okay, but hasn't changed by a great amount. In other words, we've stayed within that buffer range. Okay, so that's one way you can calculate the pH of a buffer if you were to, say, add an acid or a base. If you added an acid, you would do a similar calculation, except you would be consuming the ion rather than the acid. Okay, so I just want you to know that that's possible. Okay, so we're going to kind of move on from there. So this next section, we're going to talk about acid-base titrations. And if we were still holding normal lab, we would learn a lot about these. We would actually do 2 or 3 of them. But for now, we're just going to talk about it. Okay, so what is a titration? So a titration is a procedure for determining the concentration of a solution by allowing a carefully measured volume to react with a standard solution of another substance whose concentration is already known. Okay, so what do I mean by this? Okay, so I want to take a burette. So a burette is those long glass tubes that you probably used in Chem 1, hopefully. Okay, and they're very finely graded. In other words, we know the volume precisely. Okay, we're going to prepare a standard solution. Okay, the standard solution is usually made from an acid or a base that's a solid, so that it can be weighed accurately or measured accurately. Okay, we form what's called the standard solution. This is known as the titrant. So whatever you load into the burette, that's known as the titrant. Okay, so then into our Erlenmeyer flask, we would add whatever our unknown solution is. So this could be an unknown acid solution, could be an unknown base solution. Generally, you titrate base into acid. Okay, but that's not always necessarily true. Sometimes you do acid into base. It just depends what you're trying to get out of it. Okay, so you would have your unknown solution in the Erlenmeyer flask, and this is called the analyte or the titrant. And generally speaking, for something like sodium hydroxide, if we're using sodium hydroxide as a base, and we're using an acid in our Erlenmeyer flask, we'll use something like phenolphthalein, but there's lots of indicators you could use. You could even use a pH meter. A lot of times we'll do that too. Okay, so that's your basic setup. So you have a burette loaded with, generally speaking, a sodium hydroxide solution or some known concentration solution of an acid or a base. And then you have your unknown in the Erlenmeyer flask. And so what you do is you slowly add the acid or the base to the Erlenmeyer flask, and you add it very slowly, and you measure how much volume of that you add, and you know the concentration. So from that, you can determine the number of moles of the acid or the base in the Erlenmeyer flask. Okay, so we know the concentration of one, and we're looking to determine the concentration of the other. And we're going to do that by knowing the number of moles we've added of either the acid or the base to our unknown. Okay, so we have a couple important things about this. So we have the equivalence point. So this is the point of the titration at which the titrant has been added and is stoichiometrically equal to the number of moles of the analyte or titrant that are present in the sample. So this means the number of moles of acid and the number of moles of base, these are exactly equal. So don't get this confused with the endpoint, because this could be a different point on the curve, and we'll look at some of these curves. But the endpoint is the point in the titration where the indicator changes color. Typically, this occurs at the equivalence point, but not necessarily. Okay, so suppose maybe we want to know how many moles of acid it takes to change a base to a certain pH, and we'll use an indicator for that. But generally speaking, the endpoint and the equivalence point are similar, but they're not necessarily the same point. The endpoint is just when you stop doing the titration. And generally speaking, that's when your indicator would change color. So for instance, if you were using sodium hydroxide and a weak base, it would be when your phenolphthalein turned pink. Okay, so let's look at some titration curves. So this would be an example of a precise titration curve. So rather than just using an indicator, we could use a pH meter. And this is an example of that. Okay, so here we have a burette loaded with a basic solution. Then we have some acid in our flask, or they're using a beaker here just to make it easier to get the pH meter in. And we have a pH meter. Okay, notice they're going to use a glass rod so that they can stir it. Okay, so this is an example of a strong acid, strong base. So in this particular instance, we have an HCl solution loaded into the beaker, and we have sodium hydroxide loaded into the burette. And if you take data points of pH as you slowly add the base to the acid, you're going to end up with a curve like this, so sort of an S-shaped curve. Okay, and this is called a titration curve. If you notice, we're going to start from a low pH of our acid. So if we have HCl, we know our pH will be close to 0, close to 1. Okay, and as we add our base slowly, you're going to see the pH start to increase until you get up to the pH of the base. Okay? And notice we have this big jump. So it's going to slowly increase, and then suddenly it's going to jump to a basic pH. So halfway in between this point and this point is your equivalence point. So the equivalence point, again, is when the number of moles of the acid exactly equal the number of moles of the base. Okay, so let's kind of walk through this a little bit. So before the addition of any of the base, so before we add any base to the solution, okay, so our pH here is going to be close to 1, and that's because we only have HCl in solution. So we don't have any of our OH minus coming from our hydroxide in solution yet. So we only have HCl. Okay, we have relatively high, we only have HCl, and it's in relatively a high amount, so 0.1 molar. Okay, so we're going to have a low pH. So we're going to have lots of H3O plus around. Okay, then as we start to add our base, so we still have excess H3O plus around, but we have less of it. Okay, so we still have enough acid to completely consume our base. So we're still going to have an acidic pH because we still have H3O plus left over. Okay, and as we start to add more and more, eventually we get to a point. So since we're using a strong acid and a strong base, we're going to get to our equivalence point, and in this case, it's going to be a pH of 7. That's true for a strong acid, strong base, but it's not necessarily true for a weak acid or a weak base. Okay, so we'll look at some of those in a moment too. Okay, so at this point, the amount of H plus and the amount of OH minus are exactly equal in being consumed and turning into water, essentially. Okay, and then as we start to add more base, now we've consumed all of our HCl, so all of our H plus is gone. Okay, so now we have excess OH minus, and as we continue at it, the solution will grow more and more basic. Okay, so there's a couple key points here. So before we've added any acid, we only have H3O plus, then we have excess H3O plus, then we have our equivalence point, so in the middle here, and then we have only OH minus. So make sure that if I was to ask you at any point in this curve, could you tell me what is present? So for instance, if I asked you this point that I'm pointing at, so what's present in solution? Well, you would know that there's some water and there's some H plus left over. Or if I told you up here, if I could ask you maybe up here, is there any H plus left in the solution? And of course the answer would be no. Okay, so what if we're dealing with a weak acid? So before we had a strong acid, strong base, but now what if we have a weak acid? So you're going to end up with a similar curve, but if you notice, our starting pH is a little bit higher since we have a little bit weaker acid, or a weaker acid just in general. Okay, so notice that our equivalence point is also at a higher pH, so we're not at an equivalence point of 7 anymore, so don't get confused there. So that's only for a strong acid, strong base. If we have a weak acid, we're going to raise that equivalence point up a bit. Okay. Now we're still eventually going to plateau if we add enough of our base. Okay, so notice that the entire curve down here in this acidic region is just sort of shifted up. And we can break down these points too. Okay, so starting out in the solution, we only have our weak acid. So we have an acidic pH, okay, just the same as we did before when we were dealing with a strong acid, but this time it's a little bit higher of a pH since we're dealing with a weak acid only. Okay, and as we start to add our OH minus, or so our base. Okay, so we're going to have still excess acid. So here we're looking at acetic acid, but it could be any weak acid. So we'll still have some acid left over. So there's enough acid in solution to completely consume the base and still have acid left over. We call this region the buffer region because if you can picture in your mind sort of writing out a reaction, we have it up top here. So we have acetic acid and water, and we also have H3O plus, so we're still in an acidic solution. So we still have H3O plus, but now we also have the acetate ion. So what have we formed? We formed a buffer. Okay, so this portion in this curve, we have a buffer. And notice that this curve sort of has a little more wiggle to it. So it's a more gradual incline compared to our strong acid, strong base. So there's a little bit more of a tolerance within this region for change in pH. Okay, so it's going to act just like a buffer solution in that region. So make sure, so if I was to ask you, where's the buffer region on a titration curve, make sure you can point this out. Okay, then we'll get to our equivalence point just like we did before. Okay, but notice this time we have a higher pH. Why? Well, because we started from a higher pH. Okay, so since we're dealing with a weak acid, strong base, we're going to have a higher pH when we get to our equivalence point. So once we have number of moles of acid equal to the number of moles of base, well, since we started from a higher pH, of course, we'll end up at a higher pH at the equivalence point. Okay, then just like with a strong acid, strong base, we're going to end up with a point where we have excess base around. So we've consumed all of the acid. Okay, so now we have excess OH minus. Okay, so we end up with a basic plateau, in other words, so it'll keep growing up to essentially to the basis pH. Okay, and again with this curve, just make sure you can identify those key points. And if I was to ask you what's present in solution at each of those points, make sure you could tell me. Okay, and depending on our Ka, we're going to shift that curve even more. So if we have a really, really weak acid, we're going to start at a more basic pH, which should make sense. So stronger the acid, the lower pH will start at. Weaker the acid, the higher pH will start at, and the higher your equivalence point will be. So if we're doing for instance, so those are instances of where we're titrating in a base to an acid. So we're starting from acidic pH and gradually raising that pH. Well, what if instead we were starting from a basic pH? So in other words, the acid would be in the burette and the base would be in the flask. So we would start from a basic pH and we would go down in pH. But notice we still have the same shape. Okay, it's just decreasing instead of increasing in pH. But you have all the same points. So you still have an equivalence point, you still have a buffer region, all that good stuff. So everything's exactly the same. It's just backwards and upside. So it's upside down, basically, and backwards. Okay, but we still have a buffer region. We still have an equivalence point. So if it's a strong acid, strong base, we would have an equivalence point of 7. But in this case, we have a weak base. Okay, so we have a pH somewhat below 7. Okay, so remember, in this case, our strong acid is going to overtake our base, essentially. Okay, so we still have a point where we have excess. So in this case, we're dealing with ammonia. So at some point we have excess ammonia. Okay, then we have our buffer region. Okay, then we have a point where our acid completely overtakes our base. Okay, so what if we have a polyprotic acid? Okay, so what if we have an acid that has more than one proton? Okay, well in that case, the curve is going to be very similar. Okay, but what you'll notice is, so here's one titration curve, and that leads straight into the next one. Okay, so we would have pKa1, pKa2, and if we kept going, if we had a third acidic proton, we could have a pKa3. Okay, and notice this pKa. So I didn't really mention this yet, but our pKa is going to be equal to the pH at 1/2 of our equivalence point. Okay, so if we find our equivalence point, so here we have pH of 6.2 or 6.02. So at our equivalence point, we have a pH of 6.02. So if we go back 1/2 by volume, so notice that here we have a pKa of 2.34. Okay, so it's not exactly 1/2 the pH. That's not how we do it. So what we do is you look for the volume at your equivalence point. So here we have a volume of 1, so maybe we added 1 ml. Okay, if you go back 1/2 that volume, so in this case we go back to 0.5, and you find the pH at that point, that is your pKa. And that's true as you continue going. Okay, so again, if I was to give you data like this, make sure you could identify the equivalence point, take 1/2 the volume, and then determine the pKa from there. But notice again, so if this was, for instance, an acid where we have 2 acidic protons, we're going to remove the first, okay, and we'll have some equivalence point. And then if we keep going, we'll eventually remove the second, and we'll have some new equivalence point. Okay, so it's just essentially 2 titration curves stacked on top of each other. If we have a third, we would have a third, fourth, fifth, and on up. But notice each time we get to this point, we have a buffer region. So a buffer region here, a buffer region here. We have an equivalence point, and then we have excess. Okay, so it's exactly like what we were talking about before. It's just now we have a stepwise kind of equation here, or a stepwise curve. Okay. So in this last section, we're going to talk a little bit about solubility. So we're not going to go as deep into this as the book does, just for the sake of time, and for the sake of sort of limiting what you have to know for the exam. There's a lot more to this, but I'm going to cover some of the important points here. Okay, so first of all, what is solubility? Okay, so if we have a saturated solution, in this case of calcium fluoride, in contact with solid calcium fluoride contains constant equilibrium concentrations of Ca2 plus and F minus. And this is because we have an equilibrium between the ions in the crystals and the ions in solution. So in other words, we're constantly forming crystallized ions, so we're forming solid calcium fluoride, and we're also forming ions. Okay, so they're crystallizing and dissolving all at the same rate. So if you remember back to when we talked about vapor pressure, how we have dynamic equilibrium, well, this is similar. Okay, so what we're dealing with when we're talking about solubility is how much of that solid will actually form ions, or how much will actually dissolve into a solution. Okay, so but it's important to understand here that if we have a saturated solution, okay, so that means it's has all of the solid dissolved that it can. We're going to make this sort of equilibrium between our solid and our ions. Okay, and we can write an equation. So we can write an equilibrium equation for this. So equilibrium constant, just as we did before. Remember that those equilibrium constants are always calculated by the products over the reactants. So in this case, we have calcium ion and fluoride ion as our products. And then our reactant side, we just have a solid. So essentially our denominator just becomes 1. Okay, so if we wanted to write KEQ for this equation, we would write something like this. Okay, so let's look at a formal definition for solubility. Okay, so solubility is just the amount of substances that can be dissolved to form a saturated solution. And this is often expressed in grams per milliliter or moles per liter. Okay, and we call this special type of equilibrium constant Ksp. In other words, constant for solubility. Okay, and it's determined exactly like you form other k values, so other k equations, where you take the concentration of the products over the concentration of the reactants, and of course you raise them to their stoichiometric coefficients. So in this case, since we're talking about a solid being in equilibrium with ions, our actual Ksp equation just becomes the concentration of the ions multiplied. Okay, so Ksp is a solubility product constant, but it's not necessarily the same thing as solubility. So it's sort of like thinking of as of a Ka or of another equilibrium constant, where it just tells us how far does this reaction lie either to the forward direction or to the backwards direction. Okay, so it's sort of like a Ka or a Kb value. Okay, so what if we wanted to write Ksp expressions for these salts? So it says insoluble salts, which might strike you as interesting. Okay, so how can I write a Ksp expression if the salt is not soluble in the first place? Okay, the answer to that is, though, even though that we call them insoluble salts, in all actuality they do dissolve to some point. So it's sort of like talking about a weak acid. Okay, so even though it's a weak acid, it still dissociates to some extent. Okay, so we can write Ksp expressions for these. So the first one, silver iodide. Okay, so first thing we have to do is we have to write out the equilibrium expression, or the equilibrium reaction. Okay, so here we'd have solid silver iodide in equilibrium with silver plus and I minus. Okay, so if we want to write a Ksp expression, we write Ksp is equal to, remember we're going to talk about just the products over the reactants, and since our reactant is a solid, we don't write it in the equation. Okay, so it's going to be just the product of the concentrations of our products over 1. So we don't have to write the 1 really. So that becomes our Ksp expression. Okay, so now you can try this one on your own. BAF2, the barium fluoride, give that one a try. Okay, so if we want to write a Ksp expression for this, again, we're going to write out our equation first, so our reaction equation, and it's going to be the products of the reactants. And again, our reactants are solid, so we can leave them off. Notice here that the fluoride is squared. So just like with other K values, we're going to bring down this stoichiometric coefficient and put it as a power of our concentration. Okay, moving on to the next one. Here we have silver carbonate. So I'll give this one a try. And again, write out your reaction equation and set up your Ksp. So products over reactants. Reactants are solid, so they get left out of the equation. And again, see, we notice that we bring this 2 down, our coefficient here, as the power here. Okay, so just like with other K values. Okay, so hopefully these are pretty easy. You just have to remember that you don't include liquids and solids in your Ksp expression, and otherwise, or in any equilibrium expression for that matter, and this should be a piece of cake. Okay, so let's look at some Ksp values. Okay, so let's show how we can use them to compare solubility. Okay, so here we have some compounds. So we have things like aluminum hydroxide, barium carbonate, calcium carbonate, and we have some Ksp values. So how can we use these? Okay, so suppose we wanted to compare the solubilities of some of these. What we have to do is we have to find like salts. And what do I mean by that? So I mean that we either have a ratio of something like 1 to 1. So we have 1 Ba plus for every CO3 minus, or 2 minus, excuse me. Yeah, so Ba2 plus and CO3 2 minus. Okay, or we have aluminum, so 1 aluminum, then we have 3 hydroxide, so we have a 1 to 3 ratio. Calcium fluoride, we have 1 calcium for every fluoride ion, so we have 1 to 2 ratio. So that's what I'm trying to say. So a like salt would be like a 1 to 2 salt, or a 1 to 3 salt, or a 1 to 1 salt. So we can compare those. If they're not similar in that way, we can't compare them. Okay, so again, we can only compare like salts. So if they are like salts, then you can use the Ksp values to determine their relative solubilities. So again, we're just looking at the ratio between the ions. So it's either a 1 to 1, 1 to 2, etc. Okay, so if they have a smaller Ksp value, they're less soluble. Okay, so this is exactly like Ka. You can think of it that way. So if I have a big Ka, again, you know that I have a strong acid. Okay, so I would have a small pH. Okay, so if I have a small Ksp value, that would be a less soluble salt. So that would be like a weak acid. You can kind of correlate those two. So a weak acid has a small Ka value, while an insoluble salt has a small Ksp value. So if you're comparing unlike salts, then you have to calculate the solubility to make this comparison. But as long as we're comparing light salts, then you can use the Ksp. Okay, so let's take a second to compare some of these. So suppose we wanted to do something like compare um, lead chromate, silver chloride, barium carbonate, and calcium carbonate. These are all insoluble salts. Okay, so first thing we have to do is we have to look, are they like salts? Okay, so here I have a 1-to-1 ratio, a 1-to-1 ratio, and a 1-to-1 ratio. So all 4 of them are like salts. So then all I have to do is look at my chart and find my Ksp value, and I can order them. Again, a smaller Ksp value, so here, chromate, 10 to the minus 13, compared to silver chloride, 10 to the minus 10. Okay, so if I have a small Ksp value, this is going to be less soluble. So 2.8 times 10 to the minus 13 is smaller than something like 5.0 times 10 to the minus 9. Okay, so that's how you can compare solubilities using similar salts. You can use Ksp, compare that way. Okay, we can do the same for 1 to 2 salts. So again, just make sure they're similar salts, and then you can compare their Ksps. Okay, so that actually will finish up what I wanted to get through for this chapter. Um, so hopefully this helped you prepare. Again, send me some feedback. Let me know how these are working for you. If you like them being on YouTube, if you'd prefer them somewhere else. Give me some feedback if I'm going too fast, too slow, what I can do to help you better. And good luck on the exam.